All right, so plug it in. Everybody changed. Now, what do we notice about the even function example that we did and the odd function example that we did? What do we notice about the variables? What part of the variables? I know what you mean. The exponents on those variables are all even. So if it's an even function, all of the exponents on the variables have to be even. If it's an odd function, all of the exponents on the variables have to be odd.
The thing came up and said it's saved. You ain't closed out again.
No, it's good. That was the last one. Good. All right, so the odd functions, all of the exponents are going to be odd. On the even functions, all the exponents are going to be even. Look at the one that's neither. It's a mix of those. Okay, so the shortcut is looking at the exponents out of that. But the real test is plugging in negative x. Okay, so there are shortcuts to that, but the real test is actually just working out f of negative x. All right, so if we've got an equation, we can test if it's odd, even, or neither. What if we just have a graph? So graphically, odd, even, or neither. So this is where that symmetry comes into place with respect symmetry with respect to the y-axis. What's that mean? What are we trying to visualize happening with the graph? If you fold it across the y-axis, it matches up on each side. If it has symmetry with respect to the y-axis, then it's even. Symmetry with respect to the origin, which means you fold it across and then down, that is going to be odd function. Anything else, if it's not symmetric in those ways, then it's neither. Okay, so try to attempt to draw a few graphs here, just some sketches. Don't even have to have ordered pairs or anything on them. So coordinate plane. That one. The odd, even, or neither. It's even. It's a parabola. The vertex is right there on the y-axis, so it folds across the y-axis, so that's even. That's a tough one to draw, but maybe we get the idea here. I folded that across and then folded it down. Would it match up? With respect to the origin, it means folded across and then down. So if I folded this piece over here and then folded this down on top of it, it would match up. So this would be an odd function. Graphically is not the best thing to test odd or evenness of functions. It's better if you got equations, but we got to be able to look at some graphs if we don't know the equation for them and decide if they're odd, even, or neither. Last one of these. Something. What do we say about that one? It'd definitely be neither. It doesn't not symmetric in much of any way there. Tough to find a line of symmetry for that one. So this one would be a neither. All right. Now, the next one, we're going to sketch a graph, and you don't have to have like tick marks or anything on your axes. I'm gonna label the points that you've got here. So this is the point -6, 0, and then this point down here is -4, -3. This point up here is 0, 2. Here's a point 3, 2. And then down here is going to be 6, -2. And I'm going to draw a graph that goes through those. So just kind of try to get it close to looking like mine. It doesn't have to be perfect. But you do need those ordered pairs. I need a straight edge. That's what I need. So you want your graph to look something like that. This should be a flat line right here. Just a straight line between those 2 points. Because they got the same y value, so the x value. All right, so on that graph, we're going to find the intervals that are increasing, decreasing, or constant. There's 3 different kinds of intervals that we're going to find there on this graph. Okay, so what would an increasing interval look like? From a low point to a high point. So it's kind of like what kind of slope? Kind of like a positive slope. Okay. So where do we see this line as we read it? When we're reading a graph, we read it left to right and bottom to top to find domain and range. So let's think about reading this graph left to right. Where do we see an increasing interval? Yeah, from this point here at -4, 3 to 0, 2. If we're going to talk about intervals, our interval that we're going to report here is the x interval for that. So what is the starting point of the increasing interval? -4, and then it stops increasing when I get to 0. And we're going to put parentheses on those because what's happening at -4? It's curving, it's changing direction, right there. So it's not a increasing spot or a decreasing spot, it's the change in direction spot. Remember seeing those maybe now you do. Okay, are there any other increasing intervals that move up and to the right as we read? No. Okay, so let's move on to the decreasing interval. Where would a decreasing interval be? From -6 to -4. Again, we're going to use parentheses there because we're not sure what's happening after this. The graph ended there, so it's just going to start at -6 and then go to -4. And then, are there any other decreasing intervals? 3 to 6. And you don't put a U between those. They're just listed separate there, 3 to 6. Okay. And then a constant interval would be what? What does that mean?
It stays the same.
Stays the same. So if things are constant, they stay the same. What would be our constant interval here? 0 to 3. Really easy concept there. What would the domain of this function be? Let's go ahead, since we talk about that a lot, let's go ahead and do the domain just for fun. And what brackets or parentheses? Brackets. Why brackets? Dots are closed in. Okay. What would be the range? Lowest y value is -3. The highest y value is 2. Brackets. So not going to lose the idea of domain and range either. Okay. Really easy concept reading a graph. Remember, read it left to right. there can be more than one increasing interval. There can be more than one constant interval. There can be more than one decreasing interval. There may not be any of one of those. Okay. You're going to have at least something going on, but you don't have to have an increasing interval. You don't have to have a constant interval. You don't have to have a decreasing interval. Just depends on the graph. Okay. Some of them will have no increasing interval because it's a decreasing function or something like that. So keep that in mind. All right. So next thing is talking about maximums and minimums. When we talk about maximums and minimums, we're talking about the y values. There are local maxes and local minimums. And that'll be over a smaller interval. So they'll say, within a small part of the graph, where's a local max or a local min. So again, when we talk about those things, we got to think x values, and y value. Maybe think ordered pair, that idea. And then we have what's called an absolute max or min. And that's over the entire domain for a problem. So absolute maxes and mins are over an entire domain, and then locals are in smaller spots. You may have several local maxes or mins, and you may have an absolute max or an absolute min for a problem, but you may not, depending on what's going on. So get out your textbook real quick. And let's look at page 234. So pull out your textbook, page 234. Let's all look at that together. We're going to look at part A first. Okay. So example H is going to be related to part A on figure 26. It's at the top of the page. And we're going to first find a local max over the interval 2 to 4. So those are the x values you're looking between positive 2 to positive 4, and we want to find the local maximum in that picture. So a local max is going to be the highest point over that interval. What is the highest point for that in between 2 and 4 in the x values? What's the ordered pair? Say it louder. 3, 6. That's the highest point. See that peak in the graph? That's a local max. All right. Let's get a local min for the second part. Over the interval 3, 5. So we're only looking between 3 and 5 on the x-axis. So that cuts down our focus to just that area. What's the lowest point in that area? 4, 4. So the ordered pair is 4, 4. Part 3, same problem, same picture. Name the absolute max and min for Absolute means across the entire domain. What's the domain of that graph? 0 to 5, okay? So the x value of 0, the y value of, or to the x value of 5 is the domain. So let's look at what is the absolute maximum. 3, 6. The absolute minimum. 0, 1. That's the lowest point across the entire domain. Highest point across the entire domain is 3, 6 for that graph. That one has absolute maximum in. If you look over there, look at picture D there on the same page. Look over there at picture D. Would that one have an absolute max? Why not? Keeps going up toward infinity, right, with the y values there. Does it have an absolute minimum? Where at? 0, 0. Okay, so it doesn't have to have an absolute max. Technically doesn't have to have an absolute minimum out of that. Look at example E, or the picture there for E. What do we notice there about that 0.32? It's not included. It has an empty circle there. Okay, so that makes a difference when you start looking at those pieces out of that. What's the little dotted red line there mean? Yeah, that line, that blue line is going to turn and go straight up. It's not perfectly straight up, but it's getting inching ever closer to that dotted red line. That's what's called an asymptote. We'll talk about that more when we get into rationals in chapter 5. But it's that's the idea. Okay, so absolute maxes and mins really, not, they don't always happen with graphs. Local maxes and mins are they're local. That idea. All right. Let's talk about what if you get an equation and you don't have a graph to look at for local maxes and mins or that sort of thing. So, example I is using the graphing utility find the local max and min for f of x equals 3x to the third minus 7x plus 1. All right, so we got a graphing calculator. We want to use it to help us find the local maxes and mins. So we're going to graph that equation. 3x to the third minus 7x plus 1. I'm going to go to y equals 3x raised to the third minus 7x. Oops. What happened there? But here. Minus 7x plus 1 in the graph. In this graph, where does it look like there's a local maximum? At the top of that little hump there, right? Where does it look like there's a local minimum? Bottom of this little trough. Okay. Now, let's get the graphic calculator to help us find that. So what we want to use is this little tool that it has. Excuse me. So hit second and then the trace button. And you should get this calculate menu to come up. Second trace. And you've got number 1 is value. That we already know how to do that. That's just hit trace and type in an x value and it gets you the y value back. 2 is a 0. Does anybody remember what a 0 is? X-intercept. It's an x-intercept. Crosses the x-axis. So that might be handy later on. 3 says minimum. 4 says maximum. 5 says intersect. That we got to have 2 lines for an intersect to use. And then this is some calculus stuff. We won't use that in here. But these other things we could potentially need to use. So let's try to find that local maximum first. So we're going to use option 4 for a maximum. So option 4. And what happens is it's asking you for a left bound, which means where am I going to start looking? on the left side, and then it's going to read it from left to right out of there. So I've got a little cursor there. It's in the middle. Yours may not be perfectly in the middle. I need to move it to the left of that maximum. I know where I can see where it's going to be. I'm going to move it to the left of it. So I'm just pressing the left arrow key until I get to the left of that. Don't get too far away from it, but just make sure you're to the left of it. And then hit enter. And then it asks for a right bound. So it needs, okay, where do I stop looking? I'm going to read this from left to right. I'm going to start where you marked, and I need to read to the right. How far? So you're going to move the right arrow key until you get to the right side of that maximum. Just past it and hit enter. And with the graphic, the color ones here, it puts these lines here and shows you, hey, this is the window you're looking at. You've created an interval to look into. And then it asks us to guess, and it actually is important that you guess because if you had a larger interval, there might be multiple maxes in there, so you need to point to the one you're looking at. So just move your cursor close to the one that you're looking for and hit enter, and it tells you exactly the ordered pair for that maximum, the highest point in between those two places that you found. So our x value is negative, go 2 decimal places, negative 0.88, and our y value would be 5.12. So there is a local max at negative 0.88, 5.12. And then I'm going to find that local min. Okay. So how do I get to the menu so that I can use the minimum tool? Second trace. I'm going to use the minimum tool, which is number 3. And then I need to move over there just to the left of where I know that local minimum is. So I know what a local minimum looks like. We do. And then I need a right bound. So I hit enter after I get to the left, move to the right, hit enter, and then it asks me to guess. Again, just get close to the one you're looking for and hit enter, and then go 2 decimal places on your values there. So it's at positive 0.88 and then negative 3.12. Does this equation have an absolute minimum? No, because the range is from negative infinity to positive infinity. So does it have an absolute maximum? No. Has local maxes and local mins, but it doesn't have absolutes. But there's using the graphing utility to find those. It just takes a little bit of practice doing that. Go back, if you forget how to do that, go back and watch the clip there on how to do that. It's really easy. All right. Running short on time today, so we may have to finish this tomorrow. But let's go ahead and get this thing in there. Average rate of change. Homeroom messed us up. We'd had just enough time. A rate of change, what is that? From Algebra 1. Slope. Change over time, yeah. So, change in y over change in x. The notation that the college book uses is a little weird, but just understand it's the same thing as you've used before. This is the Greek letter delta. Delta y over delta x. Delta in math means change. So change in y over change in x. So f of b, remember f of x is the same as y. So this is the y value when x is a certain number minus the y value when x is a different number. And these are the x values subtracted. It's the slope formula in disguise. That's all it is. I don't care if you remember this notation or not. Just know, you better know your slope formula. I mean, you've been doing it for 7 years now, or 5 years, something like that. So not a hard thing. Now, where it gets a little bit more complicated is when we put it in the college context. We want to find the average rate of change for f of x equals 2x squared minus 5x over the interval one, 5. Interval notation there from 1 to 5. What are 1 and 5? They're x values. x1 and x2. So to find the slope or the average rate of change, I need what? I need y values to go with those. I need ordered pairs. I need 2 ordered pairs to find the slope, right? So I've got x values coming from the interval, so I need to find the y values that go with them. So to find the y value that goes with 1, I plug it in, right? And work it out. It'll be 2 minus 5, negative 3. So f of 1 equals negative 3. And then I find f of 5. Be 2 times 25 is 50. Minus 25. 25. So f of 5. Now I have ordered pairs, and all I got to do is the slope formula to find that average rate of change. So 25 minus negative 3 over 5 minus 1. 28 over 4, which is 7. The average rate of change for that function over that interval is positive 7. That's what we're finding. Okay. Now, we will finish up tomorrow. Got 2 more examples, and we don't have time to do those, so we'll finish those tomorrow.